So at the heart of every intelligent agent, we will find the perception subsystem. As we saw in an earlier video, where the agent was actually moving in a very dynamic environment, in a kind of a self-driving car application, the perception subsystem is very essential into enabling the agent to understand its surroundings. So today, in this video, we will see this subsystem in detail, and we will outline what is inside it, which is really essentially a prediction machine. So we will be designing this prediction machine together, and one block at a time. I will start with a block diagram, the block diagram that Vapnik put together many decades ago while he was working in Bell Laboratories. This block diagram is really the block diagram that outlines the essence of supervised learning as well. So we'll see that in a moment. The Vapnik block diagram is now going to be drawn block by block, starting from the first block, which I will call the data generator. And this data generator is effectively encompasses everything that nature can generate. Nature generates images, sounds, all sorts of structured and unstructured data. And we will be calling whatever it is being generated here with X, with this kind of underbar. And this underbar will indicate that X belongs to the set of real numbers to the power of n. That's a kind of a common notation that indicates that X is, in fact, let's say a vector with n elements. Okay, so the x's are going to be mapped from the second block, which is actually called the target function, into a set of what we'll call labels, y. And these labels are going to belong into two types. The first type we will see a bit later is when y is a real number. And in this case, we'll see that this corresponds to the so-called regression problem. And the second case is when y belongs to a set of distinct classes, let's say capital K classes, total. And in this case, we will see that this corresponds to the classification problem. All right, so this is basically, and so let's sort of give an example of regression, an example of classification. Let's assume that X is square footage of the house, the number of bedrooms, the number of bathrooms, and Y will correspond to the price of the house. That is sort of a use case that governs regression. In the case of classification, X would be an image, and we want to understand whether this image represents a person, there is a person in that image or not. And that's a classification problem. It's a binary classification problem. Now there is an infinite amount of data that nature can generate. So what we have to do over here and is to introduce a new block that we will call the sampler, or the sampling block. So the sampling block is effectively out of the infinite mappings of X and Y, samples few that we will actually call with this kind of calligraphic D symbol, and it will be called a data set. And the data set brings together examples, which are pairs of x and y, and where I is in the sort of set of numbers from 1 to m. So from now on, we will have m examples that the sampling block is actually giving to us. And it's worth noting that the sampling, we have absolutely no control about the sampling or any blocks above this line. So the sampler will play a couple of tricks for us. The first, to understand that, let's assume the first use case where you're given a data set that contains 100,000 images of people that are healthy from the, let's say, the CAT scans, and 10,000 images of people that are unfortunately have a cancerous condition. And as you can understand, the predictor will actually need to be very accurate in detecting the cancerous cases. This is a major problem in machine learning in general, and it's actually called class imbalance in our data set, and we will learn how to deal with such problematic data sets shortly. The second case is that of missing data. In the case of missing data, we have x's. Let's say back to the house price prediction problem. Here you have x represents a house. It has several features: the square footage, the number of bedrooms, number of bathrooms. And for some of those examples, some of those houses, there is absolutely no information about the number of bedrooms. The square footage is also missing. Yes, that's basically the well-known missing data problem. And this is yet another trick that the sampler will play for us. Now that we have, seen what the sampler will give us, let's now start designing our predictor machine. First block, according to Vapnik, that we need to specify, I will draw it right down here at the bottom of this diagram. And this actually is called hypothesis set. So the hypothesis set is our own guess about the nature of this target function. So we're trying to guess what it is. That's what we need to do. And the function had an argument x, if you remember. For our hypothesis, we will also include a set of parameters. So it's going to be a parametric function. From now on, the set of parameters is going to be in general called W. In some instances, we'll call it theta later on as well. But for now, let's keep it at W. And actually, later on in the next video, we'll start plotting some of these parametric functions to understand exactly how W, what kind of degrees of freedom it provides to us. So for now, think about the G as something that will ideally resemble F. And how can we actually resemble a function we have absolutely no information about it? So we'll see how that goes. So let's now draw the other block, which I will draw over here in the middle. And so this block, I want to call this block the optimization algorithm. The optimization algorithm is going to do a couple of things for us. So it will receive the data from the top. It will also receive a hypothesis set. And with the help of another block, which is, I will draw it over here on the left, which I will call it the objective or loss function. It will provide some information to that objective loss function block, and it will that block will respond back as to how well this parametric function g, which is our hypothesis, matches the target function f. And it will do its thing, and we'll see that it's going to be an iterative algorithm. And at some point, the iterations will end, and we will produce the so-called optimal parameter vector W. And using that, we will form our final hypothesis. This final hypothesis we will effectively corresponds to the prediction, and from now on the prediction is going to be called y hat. The hat stands for predicted, and because we are trying to predict the label y for an x that we have never seen before, so we need to understand how this x is that we've never seen before. This is will arrive to our sort of a prediction machine, and actually what will turn out is that we will need to do something in the data set to split it up into things that we will be using for running this iterative algorithm, and then things that we will do later in order for us to test exactly how close we are in our predictions and our approximation to the target function.